Hi guys, here is MIH. This open access research paper published on RSC advances you're seeing right now is the final product of a 2-year long investigation completed almost entirely by myself in institute laboratories. After 2 years since I accomplished the core work of the study, and 1 year after I responded to editorial comments with additional self-design experiments, I believe that the paper's research findings have stood against the test of time as well as my own reflections over the months. I thought now is a great opportunity to share this new and unique method of alkyl oxidation, as well as countless insights and obstacles during the process, with many more chemistry and material science enthusiasts. This video is going to focus on the synthesis and characterization of a heterogeneous catalyst that is simultaneously capable of forming stable water and oil emulsions, which means that the alkyl oxidation reaction can now occur at the interface of organic and aqueous phases, facilitating the use of eco-friendly and cheap oxidizing agents such as hydrogen peroxide instead of expensive and toxic reagents like pyridinium dichromate and desmartem peraldenane. What is even more magical with this catalyst, which I'll demonstrate in future videos, is that the emulsion formed can be packed into a flow reactor just like a chromatography column. As alcohol is added at the top, the aldehyde is released at the bottom with little to no overoxidation to carboxylic acid. No expensive reagents, no complex workup, no close monitoring, and the system can run 24/7 in a continuous flow manner to convert alcohols to pure aldehydes. It really does sound like magic, right? Now, let's see in detail how this unique catalyst is made. We'll start by preparing dendritic mesoporous silica nanospheres, or DMSNs for short, which are essentially very small spheres composed of silicon dioxide that have lots of spikes similar to a hedgehog. This shape creates tiny similar-sized pores within the spikes that can host heterogeneous catalytic sites while offering an extremely large specific surface area to greatly enhance catalytic efficiency. The silica nanoparticles are prepared by the hydrolysis of tetraethyl orthosilicate in ethanol, which is the standard method, but a precisely controlled mix of cetyl-trimethylammonium tosylate and triethanolamine surfactants must be added to form the unique and orderly spherical structure that we want. It's really interesting on that even just changing the anion from tosylate to bromide can significantly alter the shape and morphology of the nanoparticle, so sticking to this recipe is key. After the hydrolysis is completed at 80 degrees C for 2 hours, the product is separated by centrifugation at 11,000 rounds per minute for 5 minutes, washed with ethanol once, and centrifuged again. The insane centrifuge speed and duration is necessary because the nanoparticles are extremely small and easily suspend in the solution, and consequently made this step by far the most annoying because I have to centrifuge a liter of liquid twice while using 50 milliliter tubes at a time. The entire washing process took me almost 2 hours, and the wet DMSNs is then sent into a multiple furnace for calcination at 550 degrees C for 6 hours. This step serves to burn away all surfactants that remain trapped within the nanoparticles, generating an empty spherical shell composed of entirely pure silicon dioxide, without other nonmetal impurities. The calcine powder, DMSNs raw, appears snow white and is a perfect catalyst support material. However, before we load it with metal nanoparticle catalysts, the DMSNs raw must undergo 2 further treatments to tune their specific properties, the first of which being an acid washing. Dilute hydrochloric acid is added to a suspension of DMSNs raw and ethanol, and the mixture is heated at 60 degrees C for 2 hours before centrifuging, washing, and drying to give DMSNs acid. Sounds very simple and seemingly unnecessary. How could a little dilute acid change anything on an inert silicon dioxide crystal? I asked my mentor this question and he was like, "This is the standard procedure. I don't know what it does, but just follow it." I mean, that wasn't the answer I expected for. Still, after looking into literature myself, I found that the acid serves to remove remaining surfactant and organic matter, but I still don't think it does anything other than maybe promoting nanoparticles to coalesce together, as the centrifugation speed and duration are much lower than before. Anyways, we proceed to the next and more critical step, a hydrophobic surface modification, which involves using an organic silane reagent to add alkyl tails to the currently hydrophilic silica surface. The most common reagent of choice is methyl trimethoxysilane, which is added to a suspension of DMSN's acid in toluene, followed by addition of triethylamine base. What is happening is that the three methoxy groups are each attacked by free hydroxyls on the silica surface, which caps these hydrophilic sites with a hydrophobic methyl group, hence rendering the entire nanoparticle hydrophobic. After refluxing under nitrogen for 4 hours, centrifugation, washing, and drying, we have some nice DMSN's methyl that is afraid of water. You can see clearly in this contact angle measurement photo that the modified DMSN's methyl has a far larger contact angle than the unmodified version, proving that it is indeed hydrophobic and thus capable of forming water and oil Pickering emulsions. The science with emulsions and interfaces will be explained in future videos, but for now, our hydrophobic nanoparticle is ready, and the only thing left is to install active catalytic sites. My mentor's group worked with this DMSN material for quite a long time, and their experience says that transition metal nanoparticles work best with it. Fortunately, many transition metals like iron, copper, and silver catalyze alkyl oxidations quite well, so for now, things do look good. I decided to make 2 batches of catalyst, each containing silver and palladium respectively. These elements are the most promising candidates among noble metals, as gold and platinum didn't work well in a preliminary experiment, and I wonder which gives the best performance. After again dispersing my DMSNs in ethanol, I dissolved some silver nitrate in it and stirred the mixture in the dark for 2 hours for even mixing. Then some sodium borohydride is added, which immediately reduces silver nitrate to silver metal that deposits on the surface of DMSNs. The old trick of centrifugation, washing, and drying is repeated, and here we have some DMSN's AG catalyst. The catalyst containing palladium is prepared exactly the same way, except that palladium chloride is used in place of silver nitrate. And here we have the 2 catalysts laying side by side, silver on left and palladium on right, ready for testing. You can see that DMSN's PD is distinctively bluish compared to DMSN's AG, which is more of a pale lilac color. I assume this is due to size difference of metal nanoparticles. Now that the catalyst is made, some characterizations must be done to confirm that we obtained the expected nanoparticle size, morphology, elemental composition, surface area, and hydrophobicity. These variables are examined by various advanced instruments. Transmission electron microscope, or TEM, offers nanometer scale images from which the particles can be visually seen as spherical and dendrite shaped, proving that we indeed made dendritic silica spheres. Energy dispersive X-ray spectroscopy, EDX, then elucidates the elemental composition of the spheres, with each element identified by their characteristic X-ray spectrum and suggesting that silver and palladium metals are indeed loaded on the catalyst. Next, the nitrogen absorption-desorption isotherm tells the specific surface area by measuring the volume of nitrogen gas adsorbed on the surface, showing the insanely large surface area to mass ratio. Finally, the contact angle measurement, as shown earlier, measures the hydrophilicity of DMSN's surface by adding a drop of water to it under high-speed camera, highlighting the effectiveness of the hydrophobic surface treatment. All of these characterization results tells us that our nanoparticle synthesis worked nicely and its properties aligned with literature. In the next video of the series, I will reveal how this catalyst can turn benzyl alcohol into benzaldehyde in a chromatography column, as well as presenting more advanced laboratory techniques such as fluorescence confocal microscopy and HPLC monitoring. See you soon.